Here you go. Today is November 4th, 2024. This is Physics 6. And let's see, I was thinking maybe we should do just chapters 3 and 4 for the exam on Wednesday. Okay, if that's okay with you, I'll change it to 3 and 4. So we have chapter 5 for the third exam. I'm concerned that there won't be enough material for exam 3. And then, just by leaving chapter 5 for the exam 3, we will have enough for it. Okay, that's what I'm thinking. Let me know what you think. Okay, and I hope it didn't spoil your planning there. Okay. Okay, that's nice to know, Molly. Okay, chapters 3 and 4, okay? Plus lab 2 and 3. Lab 2 and 3. Now, we did lab 5. Okay, I'm gonna put it here. Oh, there will be a holiday after the exam next week. In 7 days, we'll have a holiday. Lab 5 due, right? Report for lab 5 is due after the exam on the Wednesday. And we're falling a little bit behind with respect to the schedule here. And let's see if we can finish work, at least the concept of work. But we should review the exam, sure, right? I was asked to review the exam. Let's do that.
Professor, I just have a quick question. I just want to make sure the exam is not going to be this Wednesday, is next week,
The
or
exam,
it's this Wednesday.
I didn't understand. I'm sorry. Repeat, please.
Oh, I just want to make sure what day we have our actual exam.
The actual exam
Mm-hmm.
is gonna be the day after tomorrow.
Oh,
Okay, the day after tomorrow is the 6th.
on Wednesday. Okay.
Okay, Wednesday. Okay, does it answer
Mm-hmm.
your question?
Yes.
Okay. Okay, so let's do a review, right? I was asked to do a review for this coming exam. Today is November 4th. This one here. And insert. Or students coming. Yeah, we're on daylight saving, right? Right now, daylight saving times started. Savings ended, not started. Savings ended this weekend, this past weekend. That was yesterday, right? Ended 11/03/24, right? We got it's bring forward, fall back. So because falls back, we got 1 hour of additional hour to sleep. That's what happened. and exam. Let's go to the material of the exam here. Okay, right here. Material for the second exam, lab 2 and 3. Labs 2 and 3. And I'm going to emphasize here, I am leaving chapter 5 for the third exam. Okay? For the third exam. So you're not overwhelmed, and also have enough material to cover on chapter 3, on exam 3. Okay. So what you have to know about the review for the exam, we're going to do that just for 1 hour, and then we keep on going with the material. For chapter 6, okay, review for exam 2, okay? Kinematics in 2 dimensions. Kinematics in 2D. There are the basic equations. The basic equations. The basic equations involve the following vectors. 1, vector position. We usually denoted the vector position by, yes, I hate when they do that. By the letter R. Okay, vector position. And then we have the vector displacement. And we denote it by the letter delta R. Okay, then we have a vector average velocity. Vector average velocity. The vector V, and then we put a subscript AVG to distinguish it from the instantaneous velocity, which is delta R over delta T. Vector instantaneous velocity, which is just the V without the average at the as subscript. And let's not forget, we put that limit sign. Limit right in here. I don't need that, but I need that. So this on here. Okay, now we're gonna get it the way I want. Okay, and should be what? Delta t going to 0. Limit of delta t goes to 0. When delta t goes to 0, the vector delta r also goes to 0. Oops, not like that. Now, vector instantaneous. Now that we have the vector instantaneous velocity, we can define another average vector. Vector average acceleration. The vector average acceleration depends on the definition of the vector instantaneous velocity. Like that, and that you're going to have delta v over delta t. And just like the vector instantaneous velocity, we also have a vector instantaneous acceleration. Instantaneous acceleration. In which we have a delta v over delta t. Okay. And I gotta put the delta v right here in the limit. And going back here, right? We have equations of kinematics in two dimensions, right? Oh, but graphical interpretations, right? Let's see, graphical interpretations. Graphical, let's go for graphical interpretations of that first. Graphical interpretation of the both vectors, right? One vector position. Well, before you go for a graphical interpretation, first, what we need? First, we need a path of the object in the 2D space, XY space, right? XY space. That's what we need. The vector position is the vector that goes from the origin of the XY axis to a point along the path of the object, right? And this vector position varies as time goes by. We can illustrate that by looking two-dimensional motion genetic vehicle right here, 2D motion. So here you go. We have this path here, the XY plane, right? And as time goes by, the object is gonna move throughout this path. Okay, sometimes it's gonna be here, later on it's gonna be here, and so on, right? Let's say initially it's here, and it moves along this path. I can even play a movie here for you after that. Right in here. That's a genetic treatment, right? First one, it starts here. That's a time t equal to 0. A little bit later on, the object is right in here. A little bit later on, the object is elsewhere, but it is still has to be still along the path, right? There you go. It cannot be outside this path, the object. And later on is going to be right in here. And so on, right? Let's play the movie. That's a time t equal to 0, time t equal to t1, t2, t3, and so on, right? In addition to that, we are going to also to have the vector's position. And I will illustrate this vector position as well. Here you go. Vector position, vector position. Here you go. This vector position, would be right in here. I'm going to denote that as the regular vector position, not just the initial, the regular genetic vector position. And the next vector position, don't forget this vector position may be a function of time, right? It's overlapping over the path in this case. And then we're going to have another vector position right in here. And another vector position. And then we can play the movie. Here you go. Vector position, vector position, vector position, and so on. We can also illustrate the vector velocity. The vector velocity and one more student coming in. 1, 2, 3, 4. Oops. Redo. Let's see. 1, 2, 3. Yeah, something. Let's see what happened here. Yeah, I pasted too many, right? 1, 2. 1, 2, 3, 4. Then we gotta have the vector velocity. When the vector and the vector velocity, found out that the vector velocity must be tangent to the path. Like that. The vector velocity may be also a function of time, may or may not be a function of time. In general, it will be. The first vector velocity here. My next vector velocity here. Let's say it's increasing in length. My third vector velocity here. Let's see, now it's decreasing, tangent to the path. Another one here. Okay. So what, right? Yeah. 1, 2, 3, 4. And then we also have the vector acceleration, which is going to be in general towards the center of the concavity. I do not know exactly in which direction is the center, would be the exact center of concavity, but it can be anywhere here, 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 right? What you cannot say that the acceleration vector is going to be in this direction. You cannot say the acceleration vector is going to be in this direction because it's away from the center of the concavity, right? So to know exactly the direction of the acceleration vector, you have to know the equations of motion, the specific equations of motion. Here you go, right in here. This one is going to be maybe like that, because the concavity increased, then you can expect the vector velocity to be longer. It's a very qualitative treatment, by the way. To have a more quantitative treatment, the concavity is decreasing. So because of that, now I can shrink this vector acceleration, right? And we have another one here. The concavity is still, genetic concavity is still in this direction. It looks like the concavity increased a little bit. And right in here at this point, you can see that the concavity is changing direction, right? Right in here at this point, you should expect that right here at this spot, you should expect that the acceleration vector is going to be 0, because you're changing the direction of the concavity somewhere around here, right? Okay, so going back to our notes, vector position is the vector that goes from the origin to the xy of the xy axis to a point along the path of the object as the object moves along this path. The vector position also moves, right? Oh, I didn't illustrate the, let's illustrate the displacement vector, right? Let's illustrate the displacement vector. I didn't illustrate the displacement vector. Okay. Displacement vector from, I have to overlap, here go, from the first point to the second point, right? You go, I'm gonna overlap, yeah, those two. That's the displacement vector. Displacement from the first point, the first position, to the next position. And I have to bring to the front this guy. Yeah. I'm gonna put that in a different color. So yeah, so it doesn't mix up with the path. I'm gonna put this one in red color as well. I don't need that. And now I'm gonna need the other point, this point here. All right. That's gonna be the other displacement vector. Strictly speaking, I should be giving different names to those displacement vectors, right? Because they're different from each other, but that's okay. Just keep that in mind. Bring to the front. I erase that. Next displacement vector is going to come from the, nope. Yeah, not the displacement vector. It's going to depend on this point. Yeah, okay. And yeah, okay. So and so on, right? Okay, displacement from one point, from each adjacent point, right? That's what the displacement vector is all about, from each adjacent point. The delta V vector is going to be one minus the other, and so on, right? So displacement the vector displacement will be from the first point to the vectors. There are several. The vectors displacement will be from the first point to the next one, to this point to the second to the third, and so on. The vector velocity will be tangent to the path. Vector velocity. And the vector acceleration will point towards the center of the concavity of the path. Okay, at a point where the concavity is changing direction, the acceleration vector will be 0. Will be 0. That's how the graphical interpretations of the above vectors. And then we have equations of kinematics in 2 dimensions. Equations of kinematics in 2 dimensions. Right? Equations of kinematics in 2 dimensions. In the genetic treatment, we usually start with the acceleration vector, acceleration vector. And then you find the other vectors. The acceleration vector, then from the acceleration vector, you go to the velocity vector. And from the velocity vector, we go to the position vector. Okay? But all those vectors, since you're dealing with 2-dimensional vectors, all those vectors have a y and x component. Go. Okay, so the acceleration vector has a x component and a y component. Like that. The velocity vector, same thing. The velocity vector has a x component and a y component. And the position vector, same thing. And the x component of the position vector, we just denoted by the letter x. The y component of position vector, just denoted by the letter y. Okay. The exact form of those components is going to depend, and I'm going to write it down here. The exact form of these components will depend on the type of motion involved, right? That's where we come up with some examples of 2D motion, okay? Like projectile motion. Examples of 2D motion. Examples of 2D motion. Projectile motion. In the case of the projectile motion, the acceleration vector has no x component whatsoever, assuming that xy and has a negative y component. Knowing that, okay, we can get the rest of the vectors. We can get their equation of motion. So in the case of the velocity vector, the component along the x-axis is going to be constant. And by constant, I mean the component along the x-axis is going to be equal to the initial component along the x-axis. And the component along the y-axis is going to be accelerated because it is accelerated, right? And by accelerated, I mean v naught y plus, not plus, is minus half gt, right? I am assuming an upward axis here. Uniform motion along the x-axis, accelerated motion along the y-axis. And once, if you learn the one-dimensional motion, that becomes, very straightforward for you, right? So what about the position vector? Gonna be initial position plus v naught x times t, right? And here is going to be initial position along the y-axis. Plus v naught yt. Wait a minute. It's not half here. Nobody picked that up, huh? It's just gt, right? The half is in this equation here. And now we have gt minus gt squared. Okay. Uniform motion along the x-axis, accelerated motion along the y-axis. That's one example. And then you can create other types. You can come up with other types of 2D motion, right? In addition to that of a projectile. And we talked about the relative velocity. Let's talk about the relative velocity now. Relative velocity. There is a very nice notation that allows you to memorize the concept of relative velocity. Okay, so consider two different referentials. Yeah, and one object. Okay, that's moving. That is moving. Two different referentials moving with respect to each other. Two different referentials, A and B, moving with respect to each other. Their velocity is given by velocity of, and I'm going to put that as a vector, by the way, velocity of referential B with respect to A, right? Which you already know that is minus the velocity of referential A with respect to B, like that. You change the subscript, you change the sign. Okay. Consider one, I'm gonna do it like that. One, two different referentials to each other, and two, an object, that is moving, that is also moving, Suppose we know the velocity, an object P, I'm gonna put it here, an object P that's moving, that's also moving. Suppose that we know the velocity of P with respect to, let's say, referential B, right? We know the velocity of P with respect to referential B, right? And we denote, and the notation will look like that, right? Okay. The velocity of P with respect to referential B A, with respect to referential A, will be given by, and go, velocity of P with respect to A is going to be velocity of P with respect to B plus velocity of B with respect to A, right? P is here, and I'm gonna put these different colors. So it becomes kind of obvious how this notation works. Right in here. Like that. Okay. And then I'm gonna do like two different situations. A, suppose we know the velocity of P with respect to referential B. Now, we're going to do all the way around, right? Suppose we know, and I'm gonna write it, right in here, okay? Right. Suppose we know the velocity with respect to A, right? The velocity of P with respect to referential B will be given by, and then you go, with respect to B. It's going to be given by, you go, B right in here, A right in here, A right in here. There's a very intuitive notation, which allows you to memorize it very easily, okay? So that's chapter 3. Now let's take a look at chapter 4. Chapter 4, forces and the laws of motion. Okay, concept of force, push or pull, and mass, quantity of matter. That's a scalar. Push or pull is a vector. I want to put it here, vector. And mass, quantity of matter, is a scalar. Is one of the basic quantities. One of the basic quantities. And the basic quantities are all, which are all scalars. Okay? Newton's first law of motion. You have to memorize that. If an object is either at rest or moving with constant velocity, comma, the net force applied to it is 0. And the reverse is also true. The reverse is also true. Okay. If the net, conversely, if the net force applied to an object is 0, comma, the object is either at rest or moving with constant velocity, like that. Then we have Newton's second law of motion, which is just an equation, nothing but an equation. And like I said before, Newton's first law of motion is just a special case of Newton's second law of motion. And because of that, I prefer to refer to this first law of motion as being as a quote, right? Law in quotes is not exactly a law, it's just a consequence of something else more genetic. Newton's second law of motion, and we're going to put it right here. Net force is equal to mass times acceleration. Mass times acceleration. And then we have vector nature of Newton's second law, okay? And by net force, what do I mean again? It's just a summation of the existing forces that are being applied to the object. I equal to 1 from 1 to n. And instead of net force here, I just put the subscript I. Vector nature of Newton's second law. Newton's third law. You have to memorize that too. Huh. Oh, that's so sad. Why is it doing that? Okay, here you go. If an object interacts, consider two objects, 1 and 2. Consider two objects, 1 and 2. Interacting with each other. Interacting with each other. Let f of 1, 2 be the force that object 1 exerts on object 2. Consider two objects, 1 and 2, interacting with each other. Interacting with each other means exerting a force on each other. If f of 1, 2, let f of 1, 2 be the force that object 1 exerts on object 2, comma, then the force that object 2 exerts on object 1, f of 2, 1, f of 2, 1 will be given by f of 2, 1 is equal to minus f of 1, 2. Okay, remember this notation here has nothing to do with this other notation, okay? With this other notation here. It's just a coincidence that the equations are the same. Okay, here VBA means one thing. Here, F21 or FAB means something else. Okay? Hmm. Ooh, like that. I'm gonna leave the other format there. Consider two objects like that. Newton's third law is 4.5, right? Huh, interesting. 4.1, 4.2. Oh, this one's supposed to be 4.3. Okay. 4.3. Okay. If this is 1.4.3, this is supposed to be 4.4. And this is supposed to be 4.5, right? This is the third law. And then we have to talk about the types of forces. Types of forces. Types of forces. Contact and non-contact. Contact and non-contact, right? The non-contact force that we have to know, the only non-contact force, let's say, okay, non-contact forces, the weight or gravitational force, okay? The electric force is a non-contact force. The magnetic force is a non-contact force. The strong force, which is a nuclear force, okay? And the weak force. You have to worry only about this one right here. Yeah, list them like that. Electric force, magnetic force, strong force, which is a nuclear force, and the weak force, which is also a nuclear force. During this course, you have to worry only about this force here, the weight of gravitational force. In Physics 7, we're going to cover those two other forces here. So here you go, gravitational force. There are two equations of there are two different gravitational, two different forms of the gravitational force. Nearby the Earth, the surface of the Earth, the gravitational force W is given by mg. Okay? For large distances from the center of the surface of the Earth or any other planet, right? Or any other planet or moon, the weight is going to be given by mg. It just happens that this G is gonna change as we go from one planet to another. On the surface of the Earth, G equal to approximately 10 meters per second square on the nearby the surface of the Earth, nearby the surface of the Earth. Like that. For other planets, G is going to be different for other planets. And Moon, G is going to be different. Far, not for large distances, far from the surface of a given object, comma, the gravitational force is given by formula. Ooh. Gravitational force is given by, yeah. Let's put it like that. Let's write down the gravitational force as W, right? Of a given object of mass, let's put it mass big M, the gravitational force applied to another object of mass M is given by G M big M divided by R squared, where R is the distance from this object, the center of those two objects, okay? Of a given object of mass M. So that's what you have to know about the gravitational force. 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, 6, 7, 8, 9, 10, 11, 12, okay? Normal force is the normal force is one of the several contact forces, okay? This force is between objects that are in contact with each other, right? Like a block and a horizontal surface. Horizontal or vertical surface. Okay, like that. Then we also have the static and kinetic frictional force. The frictional force, the force of friction is another contact force, okay, that opposes the motion of an object. Oppose the motion of an object. Oppose the motion of an object. Let's see. The force of friction is another contact force, right? The force of static friction prevents an object from moving. It's better like that. An object from moving. Okay? If an object is at rest, if an object is at rest, there are two forces of friction. The force of static friction prevents an object from moving. If you apply a force to this object and it does not move, it means that the force of static friction has a direction contrary to that of the applied force, right? We can do like that. You go force, organize it even better, right? Force of static friction. We usually denote that by F sub S. Like that. No, better. F sub S, lowercase s subscript. Static is another contact force. The force of static friction prevents an object from moving. If you apply a force to this object and it does not move, it means that the force of static friction has a direction contrary to that of the applied force. Has a direction contrary to that of the applied force. Okay. The force of static friction has a range of values. Okay. In other way, the force of static friction can have a value anywhere between 0 and a maximum value, that we denote as being Fs max. This maximum value is written down in terms of a coefficient that depends on the surface, the coefficient of static friction, and the normal that the object is being subjected to, like that, where, where here is going to be symbol and the coefficient of static friction mu sub f, the coefficient of static friction mu sub s, depends on the nature of these two surfaces that are in contact with each other. Okay, like that. Remember, the force of static friction depends on the force of applied friction. Okay, that's what you have to know. And it can have a value anywhere between 0 and this maximum value. It doesn't have a single value. It has a range of values. And you should have an equal sign here too. I'm gonna put like that. Okay. Which let me see if I can make it look nicer. I wanna make it look nicer. Insert. Equation. Let's see. Right in here. That's how I want it. and another one here. All right. Now we also have a force, the force of kinetic friction. Force of kinetic friction, right? The force of static and kinetic friction. They are contact forces, okay? I'm gonna need that here now. The force of static friction prevents an object from moving. If you apply a force to this object and it does not move, it means that the force of static friction will have a direction contrary to that of the applied force and same magnitude. And same magnitude. Force of kinetic friction. Oh, kinetic friction right here. I'm gonna copy that. It's not gonna be exactly, but gonna help me. The force of kinetic friction is always contrary to the direction of motion of the object. Is always contrary to the direction of motion of the object. In other vectorial format, we can write like that, you know. Let's see. Here you go. Force of kinetic friction, right? And I'm going to put it in vectorial notation. Equal. No, it's not going to be equal. I'm going to put the proportional. I'm going to put the proportionality factor here. This one. Here you go. It's going to be proportional to the velocity vector, right? Well, not exactly the velocity vector. It's the unit of the velocity vector. Okay, because it's against the motion of the object, the force of kinetic friction must have a direction that's contrary to the unit velocity vector. Okay, and that's in a vectorial format. The force of kinetic friction has just a single value. Unlike the force of static friction, unlike the force of static friction that has a range of values, okay? The force of kinetic friction has just the force of kinetic friction has just a single value given in terms of the coefficient of kinetic friction and the normal force So go the equation for the force of kinetic friction is going to be given by mu sub k times the normal, right? Or if you want to put that in vectorial format, it's going to be like the following. F sub k is equal to minus, right? Mu sub k times n times the unit of the vector velocity. The unit of the vector velocity. Right? Here we're just giving the magnitude of the. I'm even going to emphasize that is the magnitude, okay? Magnitude. Like that. And we can do the same for the normal, right? We can do the same for the normal. Like that. So now we don't need that anymore. Tension is another. Tension force is another contact force. If you tie a string to an object and apply a force to this object by pulling the string, the force on the string is the tension force. And then there are other forces. Okay, equilibrium application of Newton's law of motion. What this chapter is all about? Different examples of Newton's first law of motion. Okay, and here, okay, and here different examples of Newton's second law of motion. That's what this chapter is all about. Second law of motion. And what you need to, how do you solve this problem, right? Let's put it here, 4.17. How do you solve these problems? Okay, how do you solve this problem? One, identify the forces. First, let's see. One, I hate that, okay. First, define your system, okay? Which can be an object or a set of objects, okay? Then identify the forces, apply it to the system, okay? By the force applied to the system. Use a free body diagram. Use a free body diagram and Newton's laws of motion to get your equations to solve the problem. Okay. That would be the view that we have. Let's see, 1 hour doing that, almost 1 hour doing that, a little bit more than 1 hour doing that, right? To get your equations to solve the problem. Okay. And you can have, depending on the problem, you may have more than one free body diagram, okay? Each free body diagram will result in a single vectorial equation, okay? That's the review. Any questions before we go for the break? Okay. How many students we have? We have 19 students here. Let's go one by one. Today is the 4th. Audrey, are you there? Audrey?
I'm here.
Okay. Brianna Carrillo, are you there? I see Brianna in my roster here, my Zoom roster. I want to put a star in her name. Jazzy, are you there? Okay, Jazzy is there. Gabriel Contreras. I don't see Gabriel here. Brianna, let's see. Okay, thank you, Brianna. Liliana Cortez. I don't see Liliana here. Molly. Thank you, Molly. Henry Kim.
Here.
Thank you, Henry. Ruth. Hello, Ruth.
Here.
Thank you. Noemi Martinez. Oh. Noemi, I don't see Noemi. Next is Danae Miller.
Here.
Thank you, Danae. Ramon Olivares.
Here.
Next is Taylor Form.
Here.
Thank you. Stephanie Ramos. I can't hear from Stephanie. I'm going to put a star here in her name. Jeremiah Reyes. Hello, Jeremiah. Okay, I'm going to put a star in Jeremiah's. Sean Rosario. Okay. Thank you, Jeremiah. Sean is here. Ali is standard. Hello, Ali. Jeremiah, let's see. Okay. I can hear from Ali. I'm going to put a star here in her name. Jason Straight.
Here.
Okay, next is Elena Trujillo. Elena Trujillo. I'm going to put a star in her name here. Ali, thank you, Ali. Ali is standard, right? Okay, Jason Valadares.
Here.
Next is Larell Williams. Thank you, Larell. Nuhamin Wanimu. Next is Aliyah Zavala. Okay, and let's see how many students we have. 1, 2 students that didn't answer, 17, 18, 19. Okay, cross check with my number there. And it's 10:07 already, yeah? So let's have our break. 10:08 a.m. plus 15, 10:23, right? Yeah, 10:23 a.m. So I see you in 15 minutes. Bye-bye. I'm back here. Let's see where we stop. We're talking about work done by a force and Okay, let's copy this thing here. And paste it. We can orient ourselves, right? Work done by variable force, we already did that. And the variable force that we did was that the force of the spring. The force, the static, the elastic force of a spring, right? So we have this difference. The equation is slightly different, but the principle of calculation is the same, okay? So the work done by two different types of force, right? One, constant force. In this case, the work is equal to F delta X. And let's not forget that we also have a cosine term, right? Cosine of theta here is delta symbol. And symbol. And then we have the work done by the elastic force, which is not constant. The elastic force is going to be given by a constant multiplied by the position of the object, okay? And this work, don't forget this W here is not weight, right? This W here is work. It's going to be half the force times the displacement. In both cases, what really matters here? In both cases, the work is given by the area below the curve F versus X. And you saw that before, right in here. Oh, where's my graph? Variable force. Let me see if I find the graph here. Huh, I don't find the graph. What happened to that graph? Strange. Okay, so I'm gonna do that from scratch, okay? I'm gonna do that from scratch. I do not know what happened to that graph. Maybe I didn't save it. Work. Work, or maybe it's here, right? And I forgot to copy and paste the other one. Maybe it's here. Yeah, it doesn't look like it's here either. Okay, so it looks like I'll have to do it from scratch. Unfortunately. Variable force. Okay, work done by gosh, That really bothers me. Yeah, I can't find it. Okay, so let's do that from scratch. Here you go. Variable force, right? Yep. Not what I want. I want something else. Okay. I'm gonna put here first constant force, right? And then constant force, work of a constant force of a constant force. Go right in here. I don't need this guy. 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 I don't need any of that. When you plot the force against the position, because we're talking about a constant force, but even better, it's not just, yeah, it must be the force parallel to the displacement, right? That's why I put F sub x. When you plot the force, and this force is constant, and the object, let's say, is moving from the origin until a given position along the x-axis, right in here. Okay. The work done by this constant, here's the force, right? The force is constant with respect to x. And the object is displacing from the origin, it's moving from the origin until another position that I'm going to call x. Makes things easier, right? In this specific case, the area below this curve is going to be the work done by the force, okay? That's why I wrote that down in my notes. Okay, the F cosine of theta is just my X component of the force, right? Is F sub X times delta X. Which is equal, here is subscript. Okay, and by the elastic force, don't forget, is Kx. Okay, the force is Kx. Let's do for an elastic force now. Or by a variable force. By a variable force. And variable, I mean the elastic force. Now, instead of being constant, it's going to increase linearly with the position, the magnitude. Here's the magnitude, okay? Here's the magnitude. So now we have to worry about the final value here. Oh. And the area below the curve is going to be this one right in here. and hatchet. Let's fill with that's the area below the curve. Area below the curve. That below the curve is, and I'm going to call the value here f sub x2. Okay? Is f sub x times x. So it's good. So 2 different ways of calculating the work done, right? By in a graphical way and mathematically. Let's get the polygon here. 1, 2, 3. Yeah. And now I'm gonna make it okay. Here I will also call this. Let's put this one here max instead of f sub x, right? Let's put that max value. Area under the curve. Is going to be f max x, and then you have half, which is the area of the triangle, right? The area of the triangle is half the area of the rectangle, of this rectangle here. That's how we interpret the area of this right angle triangle. Like that. Are we recording? Let's see. Oh, yeah, we are recording. That's good. That's what you have to know. So we're done with this one and this one. And now let's talk about this one here. The work kinetic energy theorem. It's a very important theorem. Very important theorem because it gives rise to the concept of conservation of energy. Okay, so recall that, well, so far we did examples, right? So far we did examples of the work done by a single force. But I also mentioned that we can find the work done by a set of forces. Okay? And then there is this very special result, very important. There is a very important corollary in physics. And corollary means consequence of something else. consequence of a law, okay? Consequence of a law or definition. There's a very important corollary in physics that relates the work done by the net force, okay? By the net force. Like that. So work done by a net force. Okay. I'm going to give you the result. Okay, the work done by the net force should be equal to the net force, the x component of the net force, right? I'm going to emphasize here, x component of the net force times delta x. And that's going to be given by something very simple, that's like that. I can prove that, we're going to prove that is going to be the half of the mass times the final velocity square minus half the mass times the initial velocity square. Okay? I can prove that, and we're going to do that right now. And the work kinetic energy, this corollary is called, the work kinetic energy theorem, where kinetic energy is this value that you see right here, right? We define that as being kinetic energy. The kinetic energy has the same units of the work. Final kinetic energy minus initial kinetic energy. So let's prove that. Okay, so here you go. Work done by the net force is equal to the net force along the x direction times delta x. But we also know from Newton's second law of motion that the net force along the x direction is going to be mass times acceleration in the x direction, right? From Newton's second law. I can do that like that. We'll do like that. From the second law, from Newton's second law of motion. Okay. But from kinematics, we also found the following relation. And then refresh your memory about this relation, right? An object that's under uniformly accelerated, right? Its final velocity is going to be given by its initial velocity square. Final velocity square is going to be given by its initial velocity square times 2a delta x. Do you remember this relation here? We used this equation in lab number 2, right? And since we are talking about the x component, let's put everything here, x component, and x component, like that. And then what I'm going to do, I want to write this a sub x in terms of the velocity, the final velocity square, right? We're going to substitute this ax right in here in the equation for the work done by the net force. So I'm going to invert this equation. V naught x goes to the other side, it changes sign. Now I want to write down a sub x, the x component of the acceleration in terms of the other terms, in terms of the other parameters. Okay, and now this equation goes right in here in the definition of the work done by the net force. Okay, substituting the above result into the definition of the net force, we get I'll keep this guy here on the left side. Okay. So it's obvious that there is the definition, right, of the work done by the net force right here. Okay. You can see that this delta x cancel out this other delta x. Okay. And you can also see that we can break it down into two terms, half mvx square minus half mvx naught square. Okay. This term here, we give a name. We define each separate term on the right side as the final kinetic energy or energy due to motion, and the initial kinetic energy. Okay. And just like we minus initial kinetic energy, okay? Energy due to motion, just like I had it right here. And now we can use this relationship to do some neat things, to solve some problems, okay? To solve some neat problems. One very interesting type of problem is that of a speeding car in the freeway. I like to share this example with my students, okay? Example, use your kinetic energy theorem, okay? A car is moving the freeway with speed v. The driver then applies the brakes and comes to a full stop in a distance d, okay? What would be the new stopping distance if the car was moving at twice the speed, okay? And it's not gonna be twice the distance. It's not gonna be twice the distance, okay? You can solve this problem using the work kinetic energy theorem, okay? Assume that the force of kinetic friction is uniform and equal in both cases. is equal, is uniform and equal. It's uniform during the stop, and independent, okay, of the velocity, of the speed of the car. So better. And then to understand this problem, you will have to making a drawing of the situation. Let's see if I have it here. No, I don't have it, so I gotta do that from scratch. Here you go. So we have the flat surface. Let's say we have, here's the y-axis, okay? Here you go, here's my car. I'm gonna draw it as a block without wheels. And it's initially moving at the velocity v. Yeah, that's the initial velocity. We apply the brakes in the car, and later on, the car comes to a full stop. Okay, final velocity equal to 0. Equal to 0, like that. Velocity equal to 0. During this time in which the car, you have the wheel locked, okay? Here is a motion diagram. During this time, when the car is coming to a stop, you're going to have the following forces acting in the car, right? You are going to have the weight of the car. You're going to have the normal. The normal being applied to the car. And you're also going to have the force of kinetic friction, right? Write it down here. Here's the normal. Here's the weight. And here is the force of static friction. Yeah. Like that. Those two forces cancel out. Not only those two forces cancel out, but the work done by the normal and the work done by the weight is going to be 0, right? So that's the situation. That's the solution. Work done, we're going to use the work kinetic energy theorem, and by the way, it's going to be, I'm gonna use the full equation. The work done by the net force is going to be the work done by the normal, the work done by the weight. I'm gonna put it here, mg, so you don't use the same letter, and the work done by the force of kinetic friction. Here is 0 because the force is perpendicular to the displacement. Okay. And here is going to be what? Here is going to be the force of kinetic friction times delta x. Okay. Oh, and by the way, because the force is contrary to the displacement, the work must be negative. Okay. And by the way, we also know that the final velocity is going to be 0, right? Since the final velocity is 0, so this term here must be 0. And now we have the following equation. Here you go. Here's my initial velocity that I call V0. I'm going to drop now the x subscript to simplify our notation. I'm going to cancel out the negative sign. I will drop, the x subscript to simplify our notation. And that's what we find for the work kinetic energy theorem. That's the relationship that we have for the first case, okay? Now, what happens? Now, what happens to this equation when we double the speed, right? Instead of 40 miles per hour, now we're going at 80 miles per hour, right? So the situation is going to be similar with a small difference. Okay, I'm going to call that the work done by the net force, but I'm going to put a prime here. Okay, I'm going to put a prime here. The work done by the normal force, the work done by the weight, the new work done by the force of kinetic friction. We know that those two is going to be 0 again because the work done, because the normal and the weight are perpendicular to the displacement. And now here, the force of friction is going to be the same because the coefficient of kinetic friction is going to be the same at either velocities. The normal is not going to change. Here you go. Here's first case, right? Solution. First case. V equal to, let's say, V0. Right? And then the second case. V equal to 2V0. Twice the speed now. Okay? The force of kinetic friction is going to be the same because it depends only on the coefficient of kinetic friction and the normal, which is equal to the weight, right? And I told you here before that you must assume that the force of kinetic friction is uniform during the stop and independent of the speed of the car, okay? The force of kinetic friction is slash the coefficient of kinetic. I'm going to put here the force is slash coefficient. Both the force and the force, assume that both the force and the coefficient of kinetic friction. Kinetic friction are uniform during the stop and independent of the speed of the car, okay? So this one, must be the same as this one here in the previous problem. What's gonna change is gonna be this delta x. This delta x, I'm gonna call delta x prime, okay? The initial velocity is going to be different too, okay? It's not gonna be V0 x. It's actually going to be Yo, gosh. What was V naught X? Now it's going to be twice V naught X. And it's going to be squared as well. Okay? So it's even better. No, it's even better instead of writing down as V naught X. Okay, we're going to write that down as V prime naught X squared. Okay? Because my V prime now is twice the previous one. That's better. That's better. Okay? And when we, okay, this guy is going to be 0 because the final velocity has to be 0. The car is coming to a stop. And what you see right in here is going to be twice what you had before in the first case. V naught X, right? Twice. And then this term has to be squared. This term has to be squared. V prime not X is going to be twice V naught X. We can continue with this derivation. Okay, this guy here is going to be given, going to be equal to this one here. But now I'm going to square both terms. Here is going to be 2 squared. And here is going to be V naught X squared. Do you see the difference now? When I told you it's not going to be twice the distance as before. We continue the derivation. Let's cancel out the negative signs first. This negative sign cancel out with this other one. This 2 squared becomes 4. The 4 cancels with the 2. Oh. The 4 cancels with the 2, becomes 2 here. The 4 cancels with the half, right? And now we have those two equations. Here's the second case, right? Twice the speed. Or twice the speed. Okay. For twice the original speed, we have the following relation. Compare that what we had initially, whereas initially the relation is the following. The relation was the following, right? Was the following. Here you go, like that. We want to know how this delta x relate to this other delta x. Okay? And what do we do? Well, we do the following. We're going to solve for f of k, okay? In this equation, we're going to solve for f sub k. When we solve for f sub k, the delta x goes downstairs. And now we use this f sub k right in here. Two equations. I'm going to put them side by side. That's my system of equations. Right? In the next step, this guy here is replaced by this one. And now we can put it right in here. This guy goes right in here. And by the way, this V naught X is the same as this other V naught X, right? I just forgot to drop let's drop the subscript here that I forgot to drop. Let's do some simplifications. See, we do not have to know the mass of the car to solve this problem. Even though I didn't tell you, I don't have to know because it cancels out. I don't have to know the initial velocity, the exact initial velocity. All I have to know is that in the second case, the velocity was twice the other velocity. And look what we get. If we double the velocity, this guy is going to the other side, right? If we double the initial velocity, the stopping distance actually quadruples. Okay? Quadruples. And you can repeat that for 3 times the velocity, 4 times the velocity. Okay? For 3 times the velocity, you're going to get 9 times the stopping distance. For 4 times the other velocity, you're going to get 16 times, 16-fold the stopping distance. Okay? So if you double your speed, the stopping distance will be 4-fold more, right? And if you do for the triple, the stopping distance, 9-fold triple. If you quadruple, the stopping distance is going to be 16-fold, and so on, and so on. Okay, that's why it is important, right? It's important to remain at or below the speed limit. Okay? It goes with the square of the velocity. The stopping distance goes with the square of the velocity. That's why. Okay. That one application, the work kinetic energy theorem. What time is that? 11:15, right? Almost 11:15. There is another important application of the work kinetic energy theorem. But before going to that, first I have to define another type of energy. There are other applications of the work kinetic energy theorem. However, before we get into that, we have to define another type of energy, okay? The potential energy. Which is energy associated with position, okay? Let's see how we have that in the book. Going back here to the book, Wiley plus. We're almost at the point of our break. So here we go, getting to the course. Here's the homework, right? 20th of November. Why is not strange? To November, huh? Okay, this one work. Okay, I still didn't. Yeah, I don't understand why this thing. Let's see here what's going on. I'll get to that later on. Let's not go on a tangent here, right? Let's go to the book. Let's talk about the book here. Launch the book. Six, work and energy. Work done by constant force. We did the work done by variable force. Work kinetic energy theorem. And the next thing that we're going to see is going to be the gravitational potential energy, okay? So it's 11:15 right now. Let's take our break. Break from 11:15 a.m. to 11:30 a.m. Am I missing any questions here? No? All right, so let's stop sharing. And if you don't have any questions, I will see you in 15 minutes. I'm back here. And let's share the screen again. Okay, and what we're going to do now, we're going to talk about conservative and non-conservative forces, and then we're gonna get to yeah, here you go. The gravitational potential energy. Okay, let's do this way. There's here's supposed to be 6, right? Yeah, it's supposed to be 6. Let me change the numbers right in here. Huh. Yeah, it's not gonna let me do that, unfortunately. Okay, supposed to be 6-1, 6-2, 6-3, okay? That's what it's supposed to be. Let's talk about conservative and non-conservative forces first, and then we talk about gravitational potential energy, okay? Okay, so now there are 2 ways of classifying forces, right? The first type of force classification is contact, and non-contact forces. That's one way. But there's another way. Another way is called conservative and non-conservative forces. 2 different ways, okay? Let's look at the definition of conservative force, okay? Conservative and non-conservative force. A force is conservative whenever we displace it along a path. A force will be conservative, let's say, will be conservative if the work done by this force, that if the work done by this force does not depend on does not depend on the path of the object. That's one way of defining, but there's another way. I think it's better the other way. Another way of defining a conservative force. Okay? Another way of defining. Another definition. Here you go. Another definition, which is similar to the one above, right? Another definition. They are analogous. The end result is analogous. A conservative force, a force will be conservative. A force will be conservative if the work done by this force along a closed path, that's the difference, okay? Along the closed path is 0, okay? Either definition, works. This one here is similar to this other one here. They are similar, but I prefer this one here. I prefer this one here. It's easier to illustrate, okay? And how do we illustrate that? Let's see here. Okay, this one. Okay, so conservative force. We can, we can get this one here. I'm gonna copy and paste right here. And it's important for you folks to memorize that, okay? So suppose that we have, I'm gonna do a movie, right? So I'm gonna get rid of that, get rid of that, get rid of that. And this is not a net force, it's just like a conservative force, 2, 3. That's the initial position of my object. And let's say a conservative force, that doesn't have, can be anywhere, This force can be anywhere. Here you go. Oh, conservative force. Conservative force. Let's do simpler than that, right? X-axis first. Everything else but the x-axis. Here you go. And I'm gonna get rid of all this grid line here and make it so ugly, right? Makes the drawing so ugly. And then we're going to put my y-axis there. Playing the movie for you. My object. Initial position of my object. Here you go. Initial position is my vector. This is the vector position. Initial vector position of the object. And I'm going to have a force being applied to this object, a conservative force, okay? If this is the initial position of the object, this other one here is going to be the final position of the object, my object. And my conservative force is still acting on the object. Can you picture that? Okay. So here, x-axis, y-axis, object, initial position of the object, and that this object is subjected to a conservative force. But then this object is going to be displaced to another position, a final position. It's still subjected to this conservative force. The conservative force can be a function of the position. That's why I changed the direction and magnitude. Okay. So we have this initial position and this final position. Now, there are multiple ways for you to get to this final position, right? The object can take a path from here to here in a straight line. The object can take this other path from here to here. The object can take this another path from here to here. Okay? So that's what my next drawing illustrates. One of the paths. Here you go. That path. I'm gonna do like that. Format shape. Okay. Here, and I'm even going to label pass 1. Pass 1. Okay. And then I'm going to illustrate another pass. This one here, pass 2. This one here I call pass 2. I'll copy that. And I'm going to get rid of this pass 1. Okay. Pass 1 and pass 2. The object is getting to the same final position, but using 2 different paths. Okay. Pass 1. Pass 1 and pass 2. Notice that you have an arrow right here, the tip of the arrow. Let me put another arrow here too. So there is no doubt, yeah, right? The object, 2 different paths. My arrow, yeah. Yeah. Okay, better. I prefer this arrow. Well, the force will be conservative if the work done by this force through this path is equal to the work done by this force through this other path. That's the first definition that you saw, okay? But there is another way of defining that I prefer, okay? Now, suppose that you go ahead and you start at this point, right? You go through that path and come back throughout the other path towards the same position. If you do something like that, the force will be conservative only if the work done through this closed path is equal to 0. Okay? So here you go. Here we have, I would rather switch it. Let's put this one pass 1 and this one pass 2, okay? Better. The work done from the initial position to the final position through this path. If the force is conservative, the work done through this path is going to be equal to the work done through this other path. The force didn't change, but the path changed. Another way of defining a conservative force is if you go through a complete closed path, and the force is conservative, and if the force is conservative, the work done through this path by the force is going to be equal to 0. And notice that I changed the direction of this path, right? And I'm gonna put another arrow there as well. Yeah. This one, I can hardly see the arrow, but you got the idea, right? That's the definition. That's how we illustrate. Okay. There are some nice examples, easier to see, that I like to show my students as well. Let's see if I find it. Okay. Okay. Okay, so why are we talking about that? Okay, why are we talking about that? Let me give some examples. Examples of conservative force. Okay. One, the weight is a conservative force. Okay. The elastic force is a conservative force. Is a conservative force. The electric force, which are going to study physics, is a conservative one. Electric force. Okay. Examples of everything else should be, most of the forces are non-conservative. Okay, let's write it down. Most of the forces are non-conservative. Friction, for instance. Friction is a non-conservative force. And I can prove that to you is a very simple example. 11:45, let's see if I can get one example already made here, so I don't have to do it from scratch for you. Okay, so oops. Give me a few minutes until I find this example, this illustration. I have so many illustrations that sometimes becomes difficult for me to find a specific slide. One that I have drawn and shown to my students many times. Okay, it's not here. Let's see here. Okay, so if I don't find it, I will have to draw it myself from scratch again. That's for material for the next chapter. Yeah, okay, so it must be down there. There's no other way. Let's see. Oh, that's the graph that I was trying to find here. See that? Conservative. Yeah, it doesn't look like it's here either. What a shame. Okay, let's see the other one. Seems I will have to draw it from scratch. Here you go. Oh boy, yeah, it looks like I have to draw it from scratch. What a terrible thing. Yeah, that's a shame. Okay, so okay, example. Let's see. Example of a non-conservative force. Okay, so I'm gonna prove to you. Okay, that's x and y axis, is that plane, right? And I'm gonna get my box. I'm going to move it from here, from its initial position here. I'm gonna move it in a closed circle. Okay, X and Y plane, we go. And I'm going to simplify the motion of this guy, okay? So you can see it more easily. Here you go. So you can see the solution of this problem more easily. And oh, yeah. So here's the past one. Here is the pass number 3, and the other two are pass 2 and 4. Notice that this object is moving in a closed pass. Okay, I'll call that pass number 1, 2, 3, and 4. And that's the samples of all paths that you're going to see. And then there is one more thing, pass number 1, pass 2, 3, and 4. And move from here to here, here to here, in the clockwise direction, okay? But as this object moves, okay, it will be subjected to a frictional force, which you already know is a non-conservative force, okay? There you go. Force of friction, which is going against the motion. Subscript. Right? As he moves throughout pass number 2, there will be a force of friction here as well. And as he moves along pass number 3, there will be another force of friction here, pointing in the other direction. Here we go. Right? And then finally, we have this other pass here, pass number 4, the force of kinetic friction will be pointing in along the other direction. And you need one more thing here that I didn't tell you. This side here has a length A. Okay. Let's put A right in here, like that. Right? From 0 to A, right? Along the y-axis. And this other path here, 4 and 5, has a length B. Length B. Got the idea? Length B. So I want to prove to you that the work done by this force of friction along this path is not zero. Along this closed path is not zero. And then I want you to prove myself on your own, right? That the work done by the weight along a path in the vertical direction, any path along the vertical direction is going to be, zero, right? As well. Okay, so what time is that? Four more minutes to go. Okay, consider as an example, consider an object moving a closed path, a closed rectangular path. This object is subjected to the force of kinetic friction. Prove that the work done by this force along this closed path is different of zero, right? Let's put that as an example. Treat that as an example. And solution. Work done along path 1, right? Work done along path 1, I'm going to call W1, is going to be minus F sub K times A. Make sense? Right? F sub K is the force of kinetic friction, and A is the length of the path. Put that right in here. Okay, and then I want to repeat work done for along path number 2. Let's get that. Path 1, path 2 is going to be also a negative F sub K times, but this time is going to be B. Along path 3, running out of time, 2 more minutes to go. And that's going to be A again, right? And along path 4, right, is going to be A. Right? Going back to the drawing. From here to here, work done by this force of kinetic friction is F sub K times this length. Work done by the force of kinetic friction is, F sub K times length B, right? Length. There you go, better. The work done throughout the full closed path, the work done through the full closed path is You go. It's going to be W1 plus W2 plus W3 plus W, we're almost done. Don't go yet, right? And then you do the math, what do you get? W1 plus W3. It's going to be minus 2f sub k times A. W2 plus W4 is going to be minus 2f sub k times B, okay? Which, by the way, is different of zero. Is different of zero, okay? Repeat the above for the weight. Along a closed path in the along a closed rectangular path in the vertical direction. Okay, like that. Okay, repeat at home. Repeat at home on your own. So that's what we have. Let's see here. Shouldn't work done by path for B multiplied by B. Let me see. Oh yeah, that's right. Thank you. Yeah, multiply by B. Thank you, Molly. I did it right here, right? Here I did right. W1 plus W3, W2 plus W4. AB, AB. Thank you. Okay, so it's 12 o'clock now, and we're gonna have an exam on Wednesday, the day after tomorrow. Don't forget only 2 chapters, right? I'll post there in Canvas. Do you have any questions? Okay, so we have office hours right now. If you have any questions, you can stay for the office hours, and otherwise, I see you Wednesday.
Thank you.
Thank you, Jude. Just take time. Santiago, Brazil. Okay.